The mantis shrimp is often reduced to a meme, the animal that punches like a bullet. But when you look at the biology and evolutionary history behind that statement, it becomes far more than a fun fact. Its power is not accidental or exaggerated folklore. It is the result of long-term selective pressure in one of the most competitive ecosystems on Earth. Coral reefs are densely populated, resource-limited environments. Food is frequently armored. Snails, crabs, and clams protected by thick calcium carbonate shells. A predator that cannot breach those defenses loses access to critical calories. Over time, certain stomatopods evolved a latch-mediated spring mechanism that stores muscular energy and releases it in an ultra-fast strike, documented at speeds exceeding 20 meters per second in some species. That strike can generate cavitation bubbles and a secondary shockwave, increasing impact effectiveness. The dactyl club's layered composite structure resists fracture, allowing repeated blows. Their sophisticated visual system aids rapid decision-making in chaotic reef light. With a fossil record extending back roughly 400 million years, stomatopods have had immense evolutionary time to refine these traits, written like a thriller, but grounded in real research. A coral reef looks like paradise from a distance, bright colors, clear water, and constant movement. But from the perspective of a small predator, it's a high-pressure battleground. Space is limited, and nearly every crevice in coral or rock is already occupied by fish, crustaceans, or eels. Food is just as competitive. Many reef animals feed on the same limited resources, and hesitation often means losing a meal. Most available prey in reef environments isn't soft-bodied. Snails, crabs, clams, and other mollusks dominate the seafloor, protected by thick calcium carbonate shells. Those shells evolved specifically to resist crushing and predation. For a small hunter, breaking through that armor requires either specialized anatomy or a different feeding strategy. The reef doesn't reward simple size or brute strength alone. It favors efficiency and speed. Prolonged struggles attract attention from larger predators that patrol the same territory. In this environment, success often depends on ending a confrontation quickly, before competition arrives or a bigger animal intervenes. Survival favors precision, not hesitation. The mantis shrimp's strike is not a simple muscle-powered swing. It relies on a biological latch and spring mechanism that stores and rapidly releases energy. Inside the raptorial appendage, powerful muscles contract slowly, loading elastic structures made of chitin and mineralized material. A specialized latch holds the appendage in place while energy builds. When the latch releases, the stored energy is discharged almost instantly. Because the motion is powered by elastic recoil rather than direct muscle contraction at the moment of impact, the strike reaches extraordinary speeds, measured at over 20 meters per second in some species. The acceleration is among the fastest recorded in the animal kingdom. High-speed imaging has shown that this rapid movement can generate cavitation bubbles in water, which collapse and produce a secondary shockwave. This stored energy system allows mantis shrimp to overcome the normal limits of muscle speed. It is a mechanical amplification strategy, enabling ultra-fast movement that would be impossible through muscle force alone. Here's the part that sounds exaggerated until you see high-speed laboratory footage. The mantis shrimp strike can move so fast that it generates cavitation. Cavitation occurs when rapid movement through water creates a sudden drop in pressure, causing water to briefly vaporize into tiny bubbles. When those bubbles collapse, they do so violently, releasing additional energy. Research from Sheila Patek's lab at Duke University measured peak strike speeds in the range of roughly 12 to 23 meters per second, depending on species and conditions. High-speed video confirmed that cavitation bubbles regularly form during powerful strikes. When the bubbles implode, they produce a sharp secondary shockwave and a brief flash of light known as sonoluminescence. This means the impact is not just mechanical contact from the club itself. Even if the initial blow glances off a shell, the collapsing cavitation bubble can add extra force. The strike effectively carries a built-in aftershock, increasing the mantis shrimp's ability to fracture hard-shelled prey. If engineers built a hammer that struck with the same acceleration as a mantis shrimp, repeated impacts would likely cause fractures or structural failure. The mantis shrimp avoids this problem because its striking appendage, called the dactyl club, is built as a highly specialized biological composite. Instead of being uniformly hard, the club has a layered, multi-scale structure designed to manage stress. Materials research has shown that the outer impact surface is heavily mineralized, providing hardness to resist deformation. Beneath that layer lies a region composed of helicoidal, or bulligand, fiber arrangements made of chitin. This twisted plywood-like architecture helps redirect and slow crack propagation. Rather than allowing cracks to travel straight through the structure, the layers deflect and dissipate energy. Studies of the dactyl club have highlighted how this organization increases toughness and impact resistance, enabling repeated high-speed strikes without catastrophic failure. The club is not simply rigid. It balances hardness and toughness in a way that spreads damage and maintains structural integrity over time. This is the deeper evolutionary explanation. In marine environments, especially reefs, many prey species evolved thicker shells and tougher exoskeletons made of calcium carbonate or reinforced chitin. Individuals that resisted crushing predation were more likely to survive and reproduce. Over time, this favored increasingly durable defenses. Prey that could not withstand pressure were removed from the population, leaving behind harder, more resilient forms. That shift created selective pressure on predators. If a predator relied on armored animals for food, it faced a clear choice: evolve a way to breach those defenses or lose access to a critical resource. For mantis shrimp species known as smashers, natural selection favored individuals capable of generating higher impact forces and resisting self-damage during strikes. As a result, mantis shrimp became specialists. They do not simply overpower prey through size. They access food sources like heavily shelled snails and crabs that many similarly sized predators cannot efficiently exploit. Their strike represents adaptation to an ecological arms race, not random excess strength. On a coral reef, the most dangerous phase of hunting often isn't the initial attack, it's the struggle that follows. A prolonged fight creates noise, vibration, and movement that can attract larger predators such as groupers, triggerfish, or octopuses. In a densely populated ecosystem, any sign of distress can quickly draw unwanted attention. For a small predator, even a successful capture can turn into a loss if a larger animal intervenes. Extended grappling also increases the risk of injury. Hard-shelled prey like crabs have claws, and struggling animals can inflict damage that compromises future survival. Energy expenditure is another factor. Repeated failed attempts waste calories in an environment where competition is constant. Natural selection, therefore, favors strategies that reduce exposure time. In mantis shrimp, the rapid strike minimizes chasing and wrestling. By delivering a decisive, high-speed blow, they disable or fracture prey quickly. The encounter ends in milliseconds rather than seconds, reducing vulnerability and improving hunting efficiency in a crowded reef system. Many people assume mantis shrimp were always powerful punchers, but evolutionary research on stomatopods suggests a more gradual story. Modern mantis shrimp fall into two primary functional groups: spearers, which use sharp barbed appendages to impale soft-bodied prey like fish, and smashers, which use a heavily mineralized club to break hard shells. Phylogenetic studies indicate that the spearing form is likely more ancestral, while the smashing appendage evolved later in certain lineages. That sequence fits what biologists would expect in an evolutionary arms race. Early stomatopods appear to have specialized in capturing softer, more vulnerable prey. As reef ecosystems diversified and armored organisms like snails and crabs became more common and better defended, selective pressure favored individuals capable of cracking shells. Over time, structural modifications to the raptorial appendage, thickening, mineralization, and the development of elastic energy storage produced the modern smashing club. In other words, the mantis shrimp did not begin as a shell breaker. It first evolved to catch prey efficiently, and later evolved the tools necessary to defeat armor. Mantis shrimp vision is widely known for its complexity, but the more important question is why that complexity evolved in the first place. Coral reefs are not visually calm environments. Sunlight passes through moving surface water and breaks into shifting patterns of glare and shadow. Waves and currents constantly alter light angles. Reflective fish scales, coral skeletons, and suspended particles scatter and polarize light in unpredictable ways. For a small predator operating at close range, this creates a visually noisy world, where missing a detail can mean losing prey, or failing to notice a predator. Mantis shrimp possess highly specialized compound eyes mounted on mobile stalks, each eye capable of moving independently. They can detect linear polarized light, and some species can even discriminate circularly polarized light. Polarization reveals information about reflections, transparent tissues, and surface orientation that ordinary color vision cannot capture. Their midband region contains rows of photoreceptors tuned to different wavelengths and polarization states, allowing rapid processing of complex optical cues. This system is not simply about perceiving more colors. It enables faster extraction of meaningful contrast in cluttered environments. When survival depends on milliseconds, striking prey accurately or assessing threats, advanced visual processing becomes a decisive evolutionary advantage. Some mantis shrimp species can detect and discriminate circularly polarized light, a rare ability in the animal kingdom. Research has shown that certain stomatopods reflect circularly polarized signals from specialized body structures, particularly during social interactions. Experiments have also suggested that circular polarization cues may play a role in behaviors such as recognizing rivals or avoiding burrows that are already occupied. This is significant because most reef predators and competitors are not known to interpret circular polarization in the same way. While many marine animals can detect linear polarization, circular polarization sensitivity appears far less common. That creates the possibility of a more exclusive visual channel, signals that are highly visible to other mantis shrimp, but less obvious to unintended observers. In densely populated reef environments, where visual displays can attract attention from predators, selective signaling offers an advantage. If communication about territory or aggression can occur through polarization patterns that fewer species detect, it may reduce unnecessary conflict or exposure. In a habitat full of potential eavesdroppers, even subtle informational advantages can influence survival and reproductive success. A mantis shrimp is not built like a generalist reef fish that can easily switch diets when conditions change. Its body plan, raptorial appendage, and hunting behavior are highly specialized. In smashing species, the enlarged dactyl club, reinforced exoskeleton, and latch-mediated strike system are all tuned for delivering repeated high-impact blows. This specialization aligns with a feeding strategy focused on hard-shelled prey, such as snails, crabs, and bivalves, food sources that require force rather than speed alone. Because mantis shrimp often defend and live within burrows, their weapon also plays a role in territorial disputes. Rapid, forceful strikes can deter rivals and help maintain control over a shelter, which provides protection from predators and a site for reproduction. In crowded reef systems, losing a burrow can mean losing security and access to resources. The ultrafast strike is therefore not a novelty. It is central to how these animals feed and compete. Specialization narrows flexibility, but it increases efficiency within a niche. In evolutionary terms, once a lineage commits to a high-impact strategy, maintaining that advantage becomes essential for continued survival. The mantis shrimp evolved its extraordinary power for the same reason many reef organisms evolve extreme traits. Coral reefs are unforgiving environments. Space is limited, predators are constant, and competition for food is intense. In such systems, hesitation can mean injury, starvation, or displacement from shelter. Over hundreds of millions of years, stomatopods diversified and refined their raptorial appendages to solve a consistent problem: how to subdue prey efficiently and defend territory without exposing themselves to prolonged danger. For smashing species, that solution became mechanical amplification. Muscles slowly load elastic structures, a latch holds the tension, and stored energy is released in a rapid strike. High-speed studies have documented velocities capable of generating cavitation bubbles in water, adding a secondary shockwave to the initial impact. At the same time, the dactyl club's layered composite structure resists cracking and distributes stress, allowing repeated high-force strikes without catastrophic failure. The result is not random aggression, but evolutionary engineering. An animal that stores energy like a spring-driven system, delivers ultra-fast impacts, and survives the forces it creates. The mantis shrimp didn't evolve power for dominance. It evolved power for survival. In the crowded and competitive world of coral reefs, hesitation meant starvation or death. Over millions of years, speed became its weapon, precision became its defense, and vision became its greatest advantage. Its strike, faster than the blink of an eye, wasn't designed to impress, it was designed to end conflict instantly. The mantis shrimp became powerful because its environment demanded efficiency, not excess. In a world where every movement mattered, evolution shaped it into one of nature's most specialized hunters,